Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, chemistry students, senior 6. Welcome back. I'm teacher Alan, still with you in the chemistry lessons. How are you? I'm very fine, still living. So today we are going to look at the second last topic, and that is chemical kinetics, unit 13 for senior 6, which is about factors that affect the rates of reaction. Unit 13. So we are starting with lesson 1, as you see directly on the slide, the rates of reaction and the factors that affect those rates. Basically, it is a part of the unit 13 as we always move. So, as I had already mentioned, our lesson 1, and that is what we are going to look at. The main focus today will be on defining rate of reaction, looking at the collision theory and how it relates with the rates of reaction. Then we have the overview on the factors that affect the rates of reaction. So those are the prominent 3 parts we are to focus on in this lesson. So as usual, we always have the key terms in every lesson. So for today's lesson, there are 3 key terms. One is rate of reaction. What is it exactly? Then effective collisions. We shall talk much more on that effective collisions. Can we have collisions which are not effective? What are the conditions to bring about effective collisions? And what is exactly collisions in terms of chemical reactions? Then activation energy. So briefly, those are the crucial terms you should not miss understanding in the whole of this lesson. And this takes us to the lesson objectives. After understanding what we shall look at and the key terms, the lesson objectives are, you should be able, by the end of the lesson, to explain collision theory and how it relates to reaction rates. Explain it. In this case, for you to explain it, you need to have mastered it. So you need to take note on that part. The second objective is to propose the possible factors that may affect rates of reaction, then go ahead and explain. Of course, the factors will come as a result of you understanding the collision theory. So let's get started on our today's content. Take a close look. You have a minute or 2. Take a close look and understand those images. Image 1, 2, 3, and 4. What are they? I'm waiting to hear from you. Some of us enjoy parties, don't we? Birthday party and so on. And we've lived to see calamities like the fires, the bush fires in different regions across the globe. And some of us were all used to rear cows, so you would have to make a fence to prevent cows and goats from moving in one farm to another, especially when they are going to attack other people's crops and gardens. So, as I said, I'm waiting to hear from you. Now let's see, what are those structures exactly imply? Let's start with image 1 and 2. We all agree image 1 is a freshly made roll of barbed wire. What about image 2? What is it? If you look closely, that is rusty roll of barbed wire. In freshly made, you see it is still having its silver color. to this brown color. So I'll pose a question very fast. How long do you think it takes or it took for this roll of barbed wire to turn from this silver color to that brown as you see? How long did it take? Take a close look. You see even this image too has some of the grass arising or sprouting within the barbed wire, indicating it has possibly been there for some time, maybe a month, maybe 2, or sometimes even a year. So those are the first 2 images we are looking at. Let's now look at that. As I said, this is basically a birthday party cake, or end of year party cake, because we enjoy partying, don't we? So I will pose a question on that part. How long do you think it would take if you use a matchbox and light these fireworks sticks to produce this frame? How long do you think it will take? A blink of an eye, pew, you'd get the light going. We've all witnessed this, haven't we? Yes, we've all. So how long does it take for these parts, basically this is combustion, to occur relative to rusting? Let me give you another case, the bush fires. We've all had an opportunity of seeing fire, whether it is in the kitchen or wherever. So imagine if the fire starts in a bush, how long will it take to spread through the whole of that area? Yes? Just a blink of an eye, a few minutes or a few hours, almost a kilometer will be burnt. Recently, there has been an outbreak of fire in the USA, specifically in California, and in a few hours, the whole village was in shambles because of the fire. So, take a look at these combustion reactions and the first reaction, which is rusting. Now, I pose the last question on this part. What conclusion can we make from these pictures? Yeah? You're looking at me. Tell me, what conclusion can you make from such pictures? Well, I know you have the answer. So, as you can see, for first case, which is rusting, it can take months. You see even the evidence, the grass is sprouting. It can take months to occur. Whereas your party celebration, lighting that firework stick, it can take just a few seconds. So, conclusions. In nature, the speeds at which reactions occur differ very, very greatly. There are some reactions which occur very fast and some which occur very, very slow. Some of the slow reactions, as we've seen, rusting, fermentation, and prominently most of the organic reactions. When we talk of fermentation, let me give you an example. Wine. Some of you have seen your parents taking wine. Some of you have seen wine being served in parties and so on. Sometimes it can take 3 to 4 or sometimes 10 years for wine to mature. So the longer it takes, the more quality it becomes. So fermentation and rusting, those are some of the slow reactions. Now come back to the other side. On the first reactions, combustion you've seen, the burning of that firework component, the bush burning. Bring it in the lab, neutralization reactions, acid and the base. If I can even bring it in here, you add an acid. Most of you know that acids are corrosive. When it comes to your body, it burns it. So imagine they put a drop of acid onto your body. What happens? Your body will be burnt and you start feeling heat now and again in a blink of an eye. So the point is reactions in chemistry, or most of these chemical reactions differ. They occur, but differ at the speeds at which they occur. So when we talk of speed, we are bringing in rate of a reaction. So in this topic, as I told you, chemical kinetics, it's just about the studies or the studying of rates of reactions and what are those factors that bring about slow reaction and faster reaction. And finally, we shall be looking at the rate of reaction in terms of the change, either in the change in amount of the reactants or products with time. As you know, for products to form, reactants reduce as products are increasing. So in details, when we come to the study of the rates, so then we shall be looking at those changes, the decrease in amount of reactants and the increase in amount of products. So basically, that is the background of chemical kinetics and the rates. Remember, we said we're going to look at collision theory and the rates of reaction. So in 1916 and 1918, the German scientists, Marx and William, thought deeper about what brings some reactions to occur. Exactly what happens. You have the base, the acid, you mix them, then the reaction occurs. What exactly happens? Or you have your glucose, add it in water, add yeast, then you get your alcohol. What exactly happens? And that is collision of reacting particles. So they set an assumption. In order for a reaction to occur, the reacting particles can be atoms, molecules, ions, whichever, must collide. But then they ask themselves, do all collisions yield to a reaction? When atoms and molecules collide, does it necessitate that they will form a product? And say, no, there must be effective collisions. So we need to understand what are effective collisions. For us to understand that, let's first look through this example. At this moment, you've already studied organic, so we have addition of hydrogen chloride to ethene to form chloroethane. This is the equation. This is an ethene molecule indicating the reacting part is on the double bonds from your organic chemistry. So let's look at the possible collisions that would occur. If we take this to be hydrogen, this to be carbon, and this to be chlorine with the hydrogen, as you see, the highlighter. Then this is the Lewis structure. At this moment, you understand that. The purpose of bringing it in is to show you the lone pairs of electrons on chlorine. Now, let's see the possible collisions that would occur between these two molecules for them to form this product. They are basically 4 possible collisions and some more. These are what we highlighted. I want us to use a pen and exactly mark. We cross if it doesn't apply, then we give a tick if it applies. I'm giving you a minute. So what do you think is the best effective collision that would yield to the product? Look at them, study them critically. Let's now interpret together. Let's look at one, this collision 1. You have the chlorine. Remember we said the chlorine as it is illustrated with the green. So you have the chlorine bouncing or colliding with carbon in between hydrogens. So will this collision yield to a product? Possibly no. Reason, this collision is not attacking on the reactive site. What is the reactive site? The carbon double bond here. So indicating an effective collision needs to be specifically on that side. So let's look at collision 2. Let's look at collision 2. A hydrogen comes and hydrogen, of course, they will collide and bounce off. That is not a reactive site. Let's look at collision 3. The chlorine comes. It is hitting at the reactive site, true, but chlorine comes with lone pairs of electrons, and the double bond has high electron density. So what will happen? They will repel, indicating the collision there won't be effective. Let's look at this. Hydrogen comes onto the double bonds. So if this collision happens, highly likely, it will yield to the product. And that is true, as the mechanism suggests. Double bonds, the electrons are donated to hydrogen, and so chlorine bond breaks, and the reaction goes through. So collision 4 becomes the effective collision. If it doesn't occur this way, then the rest are not happening. Now, this takes us to see what are those factors that lead to effective collisions. If you want to get the product, then the collisions must happen within the molecules at a favorable arrangement to allow atoms and electrons to form new molecules. Like as we said, the hydrogen must collide with the double bonds because they are the ones with the electron density. And the second factor is the colliding particles should have enough energy to break the pre-existing bonds, and that is what we call activation energy. So when we talk of activation energy, the minimum amount of energy for the colliding reactant molecules must have to form the product. This is what we imply. If you have your reactants, they must have a certain energy, potential energy, and the reaction progress. For them to form products, this barrier must be overcome, the activation energy. And this case is that energy which will help in breaking the pre-existing bonds. Then you form new bonds. Whether it is exothermic or endothermic, there is that barrier. And as you can see, the barrier is higher with endothermic reactions. You looked at that in your thermochemistry. We don't need to repeat it. So the point here is colliding molecules must be oriented in a way to allow rearrangement of atoms and the electrons in new molecule, and the collision should happen with sufficient energy. So if those two happen, then effective collisions will occur. So this takes us to exactly what is the collision theory. It states that the rate at which a chemical reaction proceeds is equal to the frequency of effective collisions. If you have more effective collisions, you already know how to come up with the effective collisions. So if you have very, very many, then highly likely the reaction is going to occur, producing enough of the products. So what does that imply? The rate of reaction depends on two factors. One, frequency of collisions, and activation energy. Meaning, if we have any factors that can bring about those two, then reaction will occur. And this takes us to look at those factors that affect the rate of reaction, or those factors that bring about high amounts of collisions, or the greater frequency of collisions, and more activation energy. I think you already know some of these factors from your ordinary chemistry. The concentration of reactants, pressure, this is for gas reactants, surface area exposed if you have a solid, light intensity, some of the reaction occur in presence of light. You can bring in your biology and talk of photosynthesis. We need temperature, because some of you know that when you're done eating, you're not supposed to go and take a shower, especially in the evening. You know that, but we shall talk about it later on in the next lesson. Then the presence of a catalyst. So basically, these factors, they bring about a change on the rate of reaction. So we are going to look at each independently and how it brings about a change. Let's start with concentration of reactants. I will pose a question unto you. How does concentration of reactants bring about a change on the rate of reaction? Before I give you my response, first tell me yours. I'm waiting. So, concentration on the rate of reaction. Increase the concentration of reactants, what happens? The rate increases. And what is the reason behind? As the molecules become too many in a container or in that volume, then the distance between them reduces, so there are high chances of collisions. And with high probability of colliding with each other, then high probability of having effective collisions. And so, highly likely the reaction will increase. And that is what happens. You see the illustration. Low concentration, increase the concentration, the distance between reacting species reduces. So, let's take a few examples. We are looking at a reaction between zinc and HCl. This is how it is balanced. This is exactly what is happening. You're having your zinc producing hydrogen gas and zinc chloride, which is colorless solution. You see part of this here. So we're having two containers. One has 1M hydrochloric acid and another has 2M hydrochloric acid. You already know what M implies. It is not a million. This is a molar solution. So in here, the acid molecules are few. Here, the acid molecules are high. So the more they are, then the higher chances of collision, and so the reaction will be faster. Basically, that is it. Another case is a formation of yellow precipitate, which is sulfur when you react sodium thiosulfate and HCl. They form sulfur, which is yellow. So when you reduce the concentration of thiosulfate, it takes longer for this X to disappear. For instance, this is at high concentration, medium concentration, at a low concentration. So when the concentration of thiosulfate is low, as you maintain the concentration of HCl, then it takes very many minutes for the reaction to occur. The reason we've seen the reacting particles, in this case the ions, are far apart. So they won't be colliding, meaning the effective collisions are at minimum. And so the reaction will take longer to be observed. So that is it with the concentration. Of course, I will definitely have to leave you with a read-ahead exercise. That was simple. That was very, very applicable. I will leave you with a read-ahead exercise. I want, when we're done, take about 15 minutes, go through this exercise. It will give you a highlight of what we are going to cover on. You've seen we've only looked at concentration, and we have other more factors, as you've seen right here. We've just finished concentration. We still have pressure, surface area, and all these factors to look at. So the read-ahead exercise I'm leaving you is to help you go and enlighten your mind. When we come to discuss, then you're not so blank. What is that read-ahead exercise saying? We're still having our zinc with HCl forming hydrogen gas. So the question is, how are these factors affecting the rate of this reaction? When you increase reaction temperature for this case, of course, the assumption in here, it is occurring at room temperature, which is feasible. Then, if you're using, what about if we're using zinc granules instead of a lump of zinc metal? Meaning you need to look for the meaning of that word lump. What will happen if we stir this container having these two components frequently? What will happen? So I want you to go and read through, bring something about the effect. Will it cause a decrease on the rate? Will it cause an increase? What will it do? Then give an explanation for whichever effect you will have given out. So that is it for today. A quick recap. We've looked at the collision theory and said for the reactants to form products, the collisions between the reacting species must be effective. Not simply colliding, but the collisions must be effective. And for them to be effective, the atoms or reacting particles must arrange themselves in a way to allow the breaking of bonds and the formation of new bonds. That is the orientation part. Then they must also collide with sufficient amount of energy, which is called activation energy. When those two are achieved, then trust me, the collisions will be effective and the reaction will occur. Exactly that is what happens in the normal fermentation, for instance. That is what happens. It is about setting up those conditions and the reaction occurs. Thank you for being part of the lesson. I'm happy to still be your teacher. Please stay safe. I want to see you in the next lesson. Bye.